All right, folks. So something I want to look at right now is this idea of modeling integers, functions, decimals, percents, and mixed numbers and applying them to solutions. The first thing I think we need to talk about is that a lot of times you'll be given information that is in a form that is not really ideal for you to use in algebra. So a lot of times you'll be given what are called mixed numbers, and what we're going to see is that it's going to be much more advantageous for us to use what are called improper fractions. So for a mixed number, an example of that is the number 4 and 3/8. Okay? And so what that means, you have 4 whole, and then you have an additional 3/8. And that's nice. It's like very easy to see that that is larger than 4 and less than 5. However, if I needed to multiply that by 5 or something like that, it can be a little bit annoying. And if I divide by 4 and 3/8, well, that's going to be quite a task altogether. So what we want to do is we want to convert this to something called the improper fraction. And it's called that because the numerator is larger than the denominator. So as you see here in this original, the 3 is smaller than 8, so this fraction, 3/8, is considered a proper fraction. So that's like it's nice to look at. So what we have to do is we have to wonder, we have to get rid of the 4 and say, well, how many eighths is that? And, well, if you think about just the number 1, 1 whole is 8/8, so 4 of those would be 4 times 8/8. Okay? And then we have that additional 3 that we have to worry about, so we have to kind of tack that on as well. And so what we are left with is 4 times 8 is 32 plus 3 squared, 35 eighths. So essentially what you're doing is you're taking the denominator and you're multiplying it by the number that's given, the whole number that's given, and then you are then adding the 3 or whatever your numerator is there. Okay? So something for you to try kind of on your own, I'm sure you would be more than capable of tackling this, would be converting, say, 7 and 8/11ths from that mixed number form to an improper fraction. Okay? So you can pause and try that if you'd like. But something else I want to mention right here is estimating. We're going to mention estimating again in a minute. But if we were asked to estimate some rather large fraction, I suppose, like 496 fifths. Okay? Clearly, just plugging it into the calculator would be the fastest way, but we are not allowed to be using calculators, so we need to have a better way. And so in this case, you want to think about multiples of 5 that you know. And so I don't mean like 5, 10, 15, 20, 25. Like, we'll be here forever doing that. But that 496 is very close to 500. Okay, so you might say that this is very close to 100, okay? Because 500 over 5 would be 100. But when you say, well, can we be better than that? You say, well, 496, that's really 4 less than 500. And so dealing with fifths, it's better to maybe look at it as being 1 more than 495. And 495 would be 99 times. So 100 is really not our best answer here. We want to estimate this as the integer 99. And so 99 times 5 would give us 495. Okay? And we will do some more estimating in a minute when we are ordering numbers. Alright, so here we want to talk about various representations of a number. And to me, what really jumps out about that is the idea of percentages. And I feel like this is going to be a very common theme. I see percents a lot on the Mtel, on the practical exams, stuff like that. And so what we want to do is we want to convert percents, because that's not always the number that we want. We want to give that as a decimal. Okay? And we also have to worry about writing these as fractions. So the idea is that we are going to have 3 different looking numbers that mathematically are all exactly the same. They're all going to be equivalent. So we'll pick something relatively easy. So let's just go with, say, 21%. Okay? Now, the easiest thing to do with a percentage is to convert it to a fraction. Because if you look at the word percent, right here, percent, you can actually break that up, and I'll even underline it, that these are really two pieces. It's where per and cent. Per is kind of like a ratio, so you see that all the time, like if you're driving in miles per hour, or it's like some cost per gallon and stuff like that. And cent means 100, so cent is in century, cent is in, like, if we have 1 cent or 1 penny, that's 1/100th of a dollar. So cent always deals with some piece of 100. So 21% literally means 21 per 100. So you can very easily write 21% as a fraction. You could actually very easily write any percentage as a fraction. And so writing that as a decimal is simply dividing by 100. And you can do the long division, or you use the trick where if you are dividing by 100, you are just going to move the decimal place over 2 spaces, because we're dividing by, basically dividing by 10 twice. So we're going to move the decimal place over twice. And that is going to leave us with the decimal 0.21. Okay, real quick, if we want something that's even larger, like 135%, okay, so that means we're growing, so it's 35% more than a whole. That's still 135 per 100, and that is a decimal be 1.35. So it's important to recognize that when you have a decimal that is larger than 1, you're dealing with a percentage that is larger than 100%. All right, so now we want to recognize equivalent representations of a number. And I've seen several sample questions like this, which would be recognizing the decimal equivalent of 4/9. Now, if this were a multiple choice question, we'd go over which questions make the most sense. I would say that half of 9 is 4.5. So this should be some decimal that's a little less than 0.5. But we can actually get a more precise answer by actually doing the long division. So 4/9 is literally 4 divided by 9. So we can just do that. I'm just going to tack on some decimals. We'll decide how accurate we want to be in a second. Clearly 9 goes into 4 0 times. We knew this was going to be less than 1. So now we want to look at this number 40, and 9 goes into 40. I believe we're going to be looking at this 4 times, because 4 times 9 is 36, and then we can subtract, and we get a 4, bring down the 0, and oh boy, we have a 40 again. So it doesn't take long to see that that's going to be a 4, and then there we're going to have a 36, we're going to subtract, we're going to get 40 again. So the way we actually write that is, instead of writing it as, well, it's going to be 4, 4, 4, 4, 4, so we could sit here really all day. You can use as many decimal places as you want. We don't really need to do that. There's much better notation, and that is the 4 with this kind of bar over it. And what that means is that that 4 repeats forever. And so that is actually much more accurate than you just writing 0.4444 and running it like 10 4s. This is actually a better notation for that. Okay. Now, another example would be, say, 7/11. And again, that's just going to be kind of a long division. And clearly 11 is going to go into 7 no times, but it does go into 76. And so that will give us 66. We subtract, we get 40. That will go in 3 times, and then we get 33. And we subtract, and we get 7 again. And so we get this kind of repeating again, where this is going to continue on. And so what happens is that this is going to go 6, 3, 6, 3, 6, 3, 6, 3, and we can actually write that with the bar over the 6 and the 3. So that means that that pattern of 6, 3 repeats forever. It's going to be 6, 3, 6, 3, 6, 3, 6, 3, 6, 3. Or I'm sorry, I forgot the decimal already. 0.636363 forever. If you'd like to pause, maybe try a quick example. I think you could certainly try 2/7 and see if that decimal is going to end, or if you're going to get to use one of those bars. Alright, so I wanted to interrupt the other slides that I had. That's why this one looks a little bit different, and throw in a problem that I feel these can be very difficult. And it's a very simple premise. They just want you to order the numbers from smallest to largest. But the trick is that the numbers will not all be the same type. Like they won't all be integers. They won't all be rationals. They won't all be fractions. And they'll mix them up like this. So as you see, we have a nice rational number here. We have a little decimal, which is kind of another rational. Another fraction, and then just an integer, and then a radical, so we have the square root. And I think the most intimidating ones are probably radicals, since we're not allowed to use a calculator. But what's really going to help us here is that we're going to use tools of estimating. And what they'll do is that the people who make this test aren't dumb. They know you don't have a calculator, so they're not going to make things completely unfair. There are very reasonable ways to order these without using a calculator at all. And so I think it's best to look at numbers like this. Well, maybe not best, but easiest. It's easiest for me to look at decimals. So I think we'll leave those integers and those decimals alone and try to come up with a decimal equivalent of all these other numbers. So if I want to look at, say, 16 fifths, if I divided 16 by 5, I could actually do that the long way and actually divide it. Or I could say that 16 is 1 more than 15. And I know that 5 times 3 is 15, so this is going to be about 3 point something. So maybe 3.1, maybe 3.2, something like that. It does end up being 3.2. But the idea is that your guess of 3.1, 3.2, 3.3 will probably be enough to answer this question. Okay? Now, moving on to 7/3, well, I know that 3 times 2 is 6, and then I have 1/3 left over. So I know it's a little bit more than 2. In fact, it's 2 and 1/3, if you want to write it as that mixed number. And then if you want to do even more division, you see that 1/3 is kind of 0.3 repeating. So this is really 0.23 repeating. That getting an exact decimal is not that bad. And so the last thing that we're left with is this problematic square root of 8. And I certainly don't know what the square root of 8 is. You probably don't know what the square root of 8 is. But we can look at numbers that we do know the square root of. So for instance, I know that 8 is clearly less than 9 but greater than 4. And why I chose those numbers is going to become very obvious in a second. So that means that the square root of 4 is less than the square root of 8 is less than the square root of 9. And so you see I chose 4 and 9 was because they are perfect squares. So I know that the square root of 8 is in between 2 and 3. But that's a huge gap. So you have to say to yourself, is it closer to 2 or is it closer to 3? And if you look, 8 is very close to 9. It's actually only off by 1. But it is, relatively speaking, very far away from 4. So it's very likely that we would assume that this strays closer to 3 than to 2. So a good guess would be that this is going to be maybe 2.7, 2.8, 2.9, but definitely not like 2.2, 2.3, 2.4. Definitely not that. It's clear that this has to be closer to 3. Okay? Now comparing all of these, we can now create a little bit of a hierarchy, and it looks like the smallest number that we have is 2.5. Looks like the next largest number we have is 7/3. So we can maybe cross those off, finish these. Then we have this kind of 2.8, so we estimated the square root of 8 to be something like that. And the rest of these are clearly larger than 3. So we have 3 and then 16 fifths. And there we go. Now what we're looking at here is kind of modeling situations with decimals, fractions, etc. And what pops to my head as being something that might be very common here is the idea of like discounts and increases. So usually in terms of percentages. So if a word problem gives you a scenario where you say that the price of an object or something like that increases by a certain amount, and so let's just say, for the sake of argument, let's pick 15%. So we're going to say it increases by 15%. It is true that 15% as a decimal is 0.15, okay? But 0.15 is 15% of the whole. So if I were to multiply by 0.15, I would get just how much is increased. And so often what we're going to have to look at is that we have to include the 1. And that 1 represents the 100%. So this is the original 100%, so maybe the original price or the original value. And then the 0.15 is the increase of 15%. Okay? Now, what you want to compare that to is maybe if something decreases. And so if you see a word like that, if you want to say that something decreases by 15%, that means it is now 15% less valuable. And so then if you make the hasty decision to just multiply by 0.15, the new price after a 15% decrease is not 15%. That is how much you are, that is how much the discount is. So if you think about it, you are actually still starting with the 100%, but now you are paying 15% less. Now looking at it that way, arithmetically, I feel like can even annoy me a little bit. So look at it this way, if you don't like that, which is very simply from the very beginning, before I even write anything down, if something is decreased by 15%, think how much is left. So if something just inherently starts at 100%, which is just the definition of it being a whole, it just being itself, if it decreases by 15%, how much are you really paying? Or how much is really left? And what's left is 85%, because that is 100% minus 15%. And that as a decimal is 0.85, which is precisely what you would have gotten if you did 1 minus 0.15. So when you're looking for numbers that will multiply, for increasing, you want to be looking for numbers that are larger than 1. And when you're looking for something to be decreased, you're looking for multiplying by a number that is less than 1. Okay, so the last thing I want to talk about is actually finding percentages real quick. And I want to highlight two very different questions that are worded dangerously similar to one another. So the first one is going to be, what is 40% of 108? Now it says, what is 40% of 108? Now, you can set this up many different ways. The way I'm going to show you is using a proportion, so using things that are equal. So I know 40% I can write as 40 over 100, because that is literally what percent means. So what is 40% of 108? So you want to see here that in the numerator we have kind of the part, okay, and in the denominator is the whole. So 40% is 40, a part of 40, out of the entire 100. So 40% of 108, you need to ask yourself, is the 108 just the piece, or is it the whole? And in this case, it is the whole. So 40% of 108 means we're looking for a number that is smaller than 108. So this would be, you can call this x, you can use whatever variable you want. And so if we wanted to solve this, we would have to multiply both sides by 100 to get rid of this 100 in the denominator, and we'd have to multiply both sides by 108 to get rid of this 108 in the denominator. And ultimately what you're going to happen in doing those two steps is you're going to do this kind of cross multiplication that maybe you remember learning years ago. And it's not like a special type of math. It is literally just a shortcut from multiplying by both denominators. So this will be 100x is equal to whatever 40 times 108 is. Now I'm not going to kind of cheat myself because you guys can't use a calculator, so I'm not going to use a calculator. So 4 times 8 is 16, so we're 32. Carry the 3, but 4 times 0 is 0, and then times 4. So we have 100x is equal to 4,320. And again, we maybe want to use that trick where if we're going to divide by 100, we're really just going to move this decimal place over twice. And that's going to leave me with x equals 43.2. So that means 43.2 is 40% of 108. And that should make sense because as you see, 108 is only a little bit bigger than 100. So we would want whatever this numerator is to only be a little bit bigger than 40. And that's what we got, and that seems very reasonable to me. Now, another question that is similar to this is that 108 is 40% of what? So again, it's the same numbers. It's set up very similarly. We still have 40%, but remember, we're still talking piece over the whole. Now in this case, the 108 is 40%, so the 108 is the smaller amount. So it is 40% of what? So we need to be looking for the bigger number, and 108 is actually the piece. So go back if you need to, but double check how these are worded, and make sure that you can see that difference. And so the same skills apply here. We're going to cross multiply, so I get 40x is equal to 10800. No need to do line division because we are, again, since we are multiplying by 100, we can move this decimal place over 2 times. So we're making this 2 decimal places larger. And now, if I want to solve, I want to divide by 40. And then a little clever way is we can cross off these zeros. We can divide everything by 10. And I get x equals, 4 goes into 10 twice, the leftover of 2, 4 goes into 28 7 times. All this comes out very nice and even. 27, oh, and then we have that extra 0. I think that seemed too small. So 108 is 40% of what number? 108 is 40% of 270. And that makes sense because 40% is a little less than half, and 270 is definitely more than double 108. So you want to look for little inconsistencies like that. So to finish, I just want to ask you a couple of questions and just find out if you can find the differences. So what I want to ask you is 9 is 60% of what number, and what is 60% of 9? Forgive me that I ran out of room there. Be very careful which one is which, in which case you are looking for a larger number, and in which case you are looking for a smaller number. Good luck.